Welcome back to trigonometry. Let's get started with sinusoidal functions and transforming them. A sinusoidal function is any function whose graph looks similar in shape to the graph of the sine function. The features of a sinusoidal functions are its amplitude and its period. The amplitude of a graph is the distance from the x-axis to the highest point on the graph. The period of a sinusoidal graph is the distance between two consecutive maximum points or the distance between two consecutive minimum points. This distance is the period of the graph. Here, it is the distance between two consecutive maximum points. This distance is also the period of the graph. Here, it is the distance between two consecutive minimum points of the graph. Now that you're familiar with the features, try to find the midline, amplitude, and period of the sinusoidal function f x equals sine x. This is the midline. It is just the x-axis, which has equation y equals 0. The highest point has a y-coordinate of 1, so the distance to the line y equals 0 is 1. In other words, the amplitude is 1. These two consecutive minimum points have x-coordinates 3 pi by 2 and negative pi by 2. The distance is 2 pi. The period is 2 pi. This means the sinusoidal function f x equals cos x also has midline y equals 0, amplitude 1 and period 2 pi. This is because the y equals cos x graph is just the graph of y equals sine x shifted to the left/right. There are ways that we can transform the graphs of sine and cosine to obtain different sinusoidal graphs. In this section, we'll explore these transformations. To explore these transformations, we'll investigate the graphs of y equals a sine x, y equals sine bx, y equals sine x minus e, and y equals sine x plus d. Here a, b, c, and d can be any number, and we'll examine what happens to our graph as we change these numbers. Let's see what happens as we change a, starting at 1 and getting bigger. When a equals 1, we're just looking at the familiar graph of y equals sine x. As the value of it changes, the graph changes. As it gets bigger, the graph stretches vertically. As it gets smaller, the graph gets smaller vertically. If a is a positive number, then the graph of y equals a sine x looks exactly like the graph of y equals sine x, just stretched/compressed vertically, so it is a units high rather than 1 unit high. If a is a negative number, then the graph of y equals a sine x looks exactly like the graph of y equals sine x, but reflected across the x-axis and then stretched or compressed vertically, so it is a, the absolute value of units high rather than 1 unit high. Now draw the graphs of y here. To get the graph of y equals 4.5 sine x, we just need to take the graph of y equals sine x and stretch it vertically so that the graph is 4.5 units high. It looks like the one on the top. To get the graph of y equals negative 1.5 sine x, we start by taking the graph of y equals sine x and stretching it vertically by absolute of minus 1.5 is equal to 1.5 units. Then we just have to reflect the graph across the x-axis to finish. It looks like the one on the bottom. Now let's look at y equals sine bx. When b equals 1, we're once again just looking at the graph of y equals sine x. As b gets bigger, the graph compresses in the horizontal direction. The peaks, troughs, and x-intercepts get closer together. For example, the graph of y equals sine x has a period of 2 pi, while the graph of y equals sine 2x has a period of pi. As b gets smaller, the graph is stretched horizontally. Once b becomes negative, the graph gets reflected across the y-axis and then starts to stretch again as b gets more negative. For example, the graph of y equals sine negative 2x is just the reflection of the graph of y equals sine 2x across the y-axis. Try and draw the graphs of y here. To get the graph of y equals sine x by 3, we just need to take the graph of y equals sine x and stretch it horizontally by a factor of 3 so that it has consecutive x-intercepts at x equals 0 and x equals 3 pi rather than at x equals 0 and x equals pi. It looks like the graph on top. To get the graph of y equals sine negative 4x, we just first need to take the graph of y equals sine x and compress it horizontally by a factor of 4 so that it has consecutive x-intercepts at x equals 0 and x equals pi by 4 rather than at x equals 0 and x equals pi. This gives us the graph of y equals sine 4x. Then we just need to reflect across the y-axis to get the graph of y equals sine negative 4x. It looks like the graph on the bottom. Now, let's look at y equals sine x minus c. When c equals 0, we're just looking at the familiar graph of y equals sine x. As c gets larger, the graph stays exactly the same shape but shifts to the right. For example, when c equals 2, the graph is the same shape as y equals sine x, but shifted 2 units to the right. As c becomes more negative, the graph stays exactly the same shape, but now shifts to left. For example, when c equals negative 2, the graph is the same shape as y equals sine x, but shifted 2 units to the left. Try and draw the graphs of y. To get the graph of y equals sine x minus pi, we need to take the graph of y equals sine x and shift it pi units to the right, since pi is a positive number. It looks like the graph on the top. To get the graph of y equals sine x plus pi by 3, we first need to realize that sine x plus pi by 3 is the same thing as sine x negative of negative pi by 3. Then we only need to take the graph of y equals sine x and shift it pi by 3 units to the left, since negative pi by 3 is a negative number. It looks like the graph on the bottom. Let's look at y equals sin x plus d. When d equals 0, we're once again just looking at the graph of y equals sin x. As d gets larger, the graph stays exactly the same shape, but shifts upwards. For example, when d equals 2, the graph is the same shape as y equals sine x, but shifted 2 units upward. As d gets more negative, the graph stays exactly the same shape, but shifts downwards. For example, when d equals negative 1, the graph is the same shape as y equals sine x, but shifted 1 unit downward. Now try and draw the graphs of y. These are the simplest of all our examples so far. To get the graph of y equals sine x plus 1, we just take the graph of y equals sine x and shift it up by 1 unit. It looks like the graph on the top. To get the graph of y equals sine x minus 2.5, we just take the graph of y equals sine x and shift it down by 2.5 units. It looks like the graph on the bottom. We can combine all these types of transformations together to get the general form of a sinusoidal equation. Any sinusoidal equation can be described by an equation. Y equals a sine b of x minus c plus d. To get the graph of this equation, we just need to take the graph of y equals sine x and stretch it vertically by a factor of a and reflect in the x-axis if a is negative. Stretch it horizontally by a factor of 1 by b and reflect in the y-axis if b is negative. Shift c units to the right if c is positive or c units to the left if c is negative. Shift it d units upwards if d is positive or d units downwards if d is negative. We would also do all the same things if we were trying to graph the equation. Y equals a cos b of x minus c plus d. Now that we are acquainted with all the transformations, try drawing the graphs of y here. Pause the video and try it. To start, we should begin with the graph of y equals sine x. To get the graph of y equals 2 sine x, we stretch the graph vertically so that it is 2 units high. Then to get the graph of y equals 2 sine x minus pi by 4, we should shift the previous graph pi by 4 units to the right. Let's learn about the amplitude, midline, and period for transformed sinusoidal functions. We already know that the graph of y equals sine x has amplitude 1. When we stretch the graph vertically by a factor of a, the distance between the midline and the maximum value is also stretched by a factor of a. So amplitude is a. We already know that the graph of y equals sine x has the line y equals 0 as its midline. When we shift the graph vertically by d units, the new midline is y equals d. We already know that the graph of y equals sine x has period 2 pi. When we stretch the graph horizontally by a factor of 1 by b, the distance between consecutive maximum points is also stretched by a factor of 1 by b. So the period of the graph is 2 pi by b. That's all for this one. I hope it wasn't too much. I'll see you in the next one.